Chapter 19. The hydrogen atom and hydrogenic ions. Section 19.4. The hydrogenic ions. Hydrogenic ions are one-electron atomic ions such as helium+, lithium-2+, and beryllium-3+, that consists of only one nucleus and one electron. The Hamiltonian of hydrogenic ions can be expressed as this: the kinetic energy operator of the single electron and the potential energy operator. The potential energy operator is negative COR because in the nucleus we have a nuclear charge of Z. Z equals 2, 3, or 4 for helium+, lithium-2+, or beryllium-3+. The 1s wave function of the hydrogenic ions is the normalization factor n times an exponential function e to the power of negative zr. Z is the number of charges in the nucleus. E to the power of negative zr decays faster than that of the hydrogen atom. We can apply the Hamiltonian operator to the wave function for those hydrogenic ions to get the eigenvalues. So we apply the kinetic energy operator to the wave function, potential energy operator to the wave function. Because the wave function does not depend on theta or phi, we have a simpler term over here that consists of only r as the variable. So mostly it's just calculus here. We take the first derivative of this exponential function, multiply by r squared, take the derivative again, and then divide by 2r squared, etc. So first, the first derivative of this, well, we get this here, and we take nz out of this parenthesis because they are constant. And then we further take the derivative of r squared times e to the power of negative zr. Using the product rule in calculus, we get this. Here we have the potential energy operator applied to the wave function. So we expand this too. We get a total of 3 terms. And fortunately, the first and third term cancel. Now we have only this. It's negative z squared over 2 times the wave function. Therefore, this function is indeed an eigenfunction of the Hamiltonian operator of the hydrogenic ions. The corresponding eigenvalue is negative z squared over 2. In general, the energy levels of the electron in an hydrogenic ion is given by this equation. E sub n is equal to negative z squared over 2n squared. Z is the number of protons in the nucleus, and n is the principal quantum number. For example, the energy of the 1s electron in lithium plus is negative 4.5. We just need to use negative 3 squared over 2 to get the energy of the 1s electron in lithium 2 plus. Similarly, the energy of the 1s electron in beryllium 3 plus can be calculated with z squared over 2, and then of course we need a negative sign in the front, and this is negative 8 atomic unit because the calculation is negative 4 squared over 2. The energy of the 2p electron in beryllium 3 plus is negative 2 atomic unit. Again, it's just negative 4 squared over 2 times 2 squared. You get negative 2 in the end. The expectation value of the kinetic energy of the electron in a hydrogenic ion is z squared over 2n squared. Note that the average kinetic energy with principal quantum number n is equal to negative total energy with quantum number n. The expression is z squared over 2n squared. The expectation value of the potential energy of the electron in a hydrogenic ion is negative z squared over n squared. the expectation value of the potential energy can be expressed as negative Z over R enclosed in a pair of brackets, because Z is a constant, so this is equal to negative Z times the expectation value of 1 over R. And this whole thing is proportional to Z squared because the expectation value of 1 over R is proportional to Z, the number of charges in the nucleus. Qualitatively speaking, the electron in the hydrogenic ion is closer to the nucleus when the nuclear charge is larger, and therefore the expectation value of 1 over R is larger when Z is larger. The energy levels of the electron in hydrogenic ions are given by this. E sub n is equal to negative Z squared over 2n squared atomic unit. The expectation value of the potential energy of the electron is negative Z squared over n squared. So you can see the average potential energy is 2 times the total energy. Both are negative. Now let's look at one example. The expectation value of the potential energy of the 1s electron in a hydrogenic ion is negative Z squared atomic unit. We can evaluate the expectation value of potential energy using quantum mechanical postulate 4. This is the expectation value of potential energy. We can take Z out, and then we just need to evaluate this negative 1 over R. Using quantum mechanical postulate 4, we have this division between two integrals. On the bottom is just the integral of the complex conjugate of the function times the function. On top, it's the complex conjugate of the wave function multiplied by, over here, the operator applied to that wave function. D tau is the volume element. D tau is r squared sine theta dr d theta d phi. So we're going to just plug in the expression for this wave function of the 1s orbital, which is n times e to the power of negative zr for the hydrogenic ion. So you can see this on the bottom 2 times, and also on the top, and over here, this is simply the potential energy operator applied to the wave function. Now we have a triple integral on top and a triple integral on the bottom. It can be separated this way. We have now a single integral of r and a double integral of theta and phi. On the bottom also we have a integral of r with respect to r, and then a double integral of theta and phi. Fortunately, the angular part of these two integrals are exactly the same, so they cancel. We have only the integrals with respect to r. And then over here we can see that this z can be rewritten as z squared times z squared over z cubed. Why am I doing this? Well, it's just I'm about to use variable substitution. I see this zr here, so I'm about to convert this r to zr, this dr to dzr. That's why I need z squared on top. I need z cubed on the bottom because I have r squared here times dr. So by doing this, I got this expression, negative z squared. Now on top and on the bottom we have two integrals with respect to zr, and we can then use variable substitution. For example, we can set x to be zr, and then we have the integral of e to the power of negative 2x x dx. On the bottom we have the integral of e to the power of negative 2x x squared dx. And we can hand derive this or get it from Wolfram alpha. And then we get the expression, it's negative z squared times 1 factorial over 2 to the power of 2 divided by 2 factorial over 2 to the power of 3. Or it's just negative z squared. So what do we have is this. The potential energy operator is negative z over r. the expectation value of potential energy is negative z squared. So now we know the 1s orbital in the hydrogenic ion has a total energy of negative z squared over 2. Its average potential energy is negative z squared. The 1s average kinetic energy then must be this total energy minus the average potential energy. Therefore, the average kinetic energy of the 1s electron in a hydrogenic ion is z squared over 2, atomic unit of energy.